I am Ramakrishna Reddy. Today we are going to discuss about some type of matrices which we are going to come across very frequently in future, and they play an important role in future, like symmetric, skew symmetric, Hermitian, skew Hermitian, unitary, orthogonal matrices. All these matrices, they're all square matrices. So in future, we take it as granted. We will never mention again and again these are all square matrices. Symmetric matrix. A square matrix A is said to be symmetric if its transpose, A transpose equal to itself. That is A transpose equal to A. By transposition, what we mean is you change the rows into columns and columns into rows, you are going to get back the same matrix. If that happens, then we say that it's a symmetric matrix. We are more interested in diagonal elements, like Aij goes as Aj and they remain same. So for a symmetric matrix, the diagonal elements, they go as the diagonal elements. And a couple of interesting results, which are pretty simple, you can prove yourself. If A is a square matrix, and if A is symmetric, then A plus A transpose is also symmetric matrix. Example, here is a symmetric matrix. 1, 2, 3, 2, 4, minus 5, 3, minus 5, 6. You transpose this matrix, you are going to get back the same matrix. So it's a symmetric matrix. Next, what is a skew symmetric matrix? A square matrix A is said to be skew symmetric if A transpose equal to minus A. That is, Aij goes as minus Aji. We are more interested in diagonal elements. So it's easy to see if you put it on the paper and do some simple algebra, then we can easily see that the diagonal elements are all 0. And vice versa is not true. That is, if all the diagonal elements are 0, then we cannot jump into a conclusion that it's a skew symmetric matrix. So for a skew symmetric matrix, the diagonal elements will be 0. A small result which we use in future. If A is a skew symmetric matrix, then A minus A transpose is also a skew symmetric matrix. So we are going to get back the same matrix, A equal to A transpose. Here is an example of a skew symmetric matrix. 0, 2, minus 1, minus 2, 0, minus 4, 1, 4, 0. It's very simple to verify. You transpose it and take a negative sign, then A equal to, we can easily see that A equal to minus A transpose. Hermitian matrix. Now we bring, along with the transposition operation, we also bring in a conjugation operation. And there is a broader matrix. And to bring complex numbers also into its purview, definition is a square matrix A is said to be Hermitian if A equal to A conjugate transpose. Some books, they also write it as A equal to A star. Star, I mean transposition and conjugation. They can be performed in any manner you like. Example, A equal to 2, 2 plus I, 4, 2 minus I, 3, I, 4, minus I, 1. You can verify. If this is A, take a transpose. Then take a transpose conjugate. You can see A equal to A conjugate transpose. So this is a Hermitian matrix. Now, in general, you take an element here, Aij goes as Aji conjugate, right? And we can easily see that the nature of the diagonal elements, they are purely real. Of course, again, the converse is not true. That is, If there is a square matrix whose diagonal elements are purely real, we cannot jump into a conclusion that it's a Hermitian matrix. Then, what is a skew Hermitian matrix? A square matrix A is said to be skew Hermitian if A equal to minus A conjugate transpose. This is also a symbol for a transposition and a conjugation. How about the nature of the diagonal elements? The diagonal Aij goes as minus Aj conjugate. So the diagonal elements will be purely imaginary. Of course, one exception, they can be zero. So the diagonal elements of a skew Hermitian matrix are either purely imaginary, including zero. Some problems. And there is a small result, which is pretty simple. We can prove that. Here it is. If A is a square matrix, then A plus A transpose is a symmetric matrix, and A minus A conjugate is a skew symmetric matrix. Sorry, A transpose is a skew symmetric matrix. Then we can write A as half times A plus A transpose plus half times A minus A transpose. Then it can be easily seen that shown that half into A plus A transpose is symmetric matrix, half into A minus A transpose is skew symmetric matrix. So any square matrix can be expressed as a sum of a symmetric and a skew symmetric matrix. Yeah, there are a couple of examples in front of you, practice problems. You can practice yourself, and it's very easy to see. Next, orthogonal matrix. This plays an important role. Square matrix A is said to be orthogonal if A transpose equal to A transpose A equal to I, identity matrix. That is, if you pre-multiply both sides by A inverse, we can also see that A transpose equal to A inverse. So the beauty in future, if you want to find the inverse, which is a tedious process sometimes, if we can find that A is an orthogonal matrix, just transpose it. Then A transpose is nothing but A inverse. So many a times we find A inverse in that way, but we need to be careful that we need to prior establish that it's an orthogonal matrix. Here is an example. You can verify yourself. Take A transpose, multiply, you will get an identity matrix. Here it is. A transpose is this matrix. A transpose equal to A transpose A equal to an identity matrix. And geometrically, it's a rotation matrix. It won't stretch. It just rotates. Okay. Now, what is a unitary matrix? To bring in complex numbers also within its purview of an orthogonal matrix, a matrix, square matrix, A is said to be unitary if A equal to A conjugate transpose or A equal to A star. Again, pre-multiplying both sides by A inverse and doing some arithmetic, we can see that A inverse equal to A conjugate transpose. So if we see that if A is a unitary matrix, then its inverse is nothing but its conjugate transpose. Example, there is a matrix in front of you, half times this, 1 plus I, 1 minus I, 1 minus I, and 1 plus I. Then take its transpose, take its conjugate, then multiply A with A conjugate transpose. Here it is. And we see that it's equal to identity matrix. So if A conjugate transpose equal to A conjugate transpose, either way you can multiply A conjugate transpose into A equal to an identity matrix, and we say that it's a unitary matrix. Unitary matrices and orthogonal matrices, they play an important role in future. right? And the column vectors, they will be mutually orthogonal, and they're of unit magnitude. And the determinant of an orthogonal matrix, to that matter, in a unitary matrix, is equal to plus or minus 1. These are the properties we make use in future. Thank you.